Hi, this is Jordan Stevens with Engineering 460, Homework 16. Unfortunately, Danica and I could not get together this weekend, so we'll be going right into it. This is the GG1 simulation. This is a queuing system problem. We're going to try to model it using simulation in Monte Carlo. So basically the first G in the GG1 describes the arrival distribution. The second part, where the second G is, describes the service distribution. And the final, the third, the one value, tells how many servers there are. So the G's described are the general distribution, and the aim of the GG1 is to find the queue length in the system. Typically, they used a Weibull distribution or a gamma distribution to simulate this model. So yeah, we're going to be using simulation to predict the GG1. So moving on, we're going to be talking about how they do it. They're going to be using a regenerative model. Basically, there are it's a state changes at discrete points in the system. So basically, we're taking note of things happening at a certain point in the system. There are three phases of the system. There are customers entering the system, customers leaving the system, and customers being served. Customers being served is a conditional phase. Basically is when a person is in a line and they're going to that one server and then they're being served. The customers entering and leaving distribution phases are based on different distribution streams. This works out pretty well for our simulation method. So we're going to be simulating the arrival time and the service time. So here we go into our actual model. So we're going over to MATLAB. So I got this simulation program out of the back of our textbook. Basically, we are taking a lambda, a mu, a gamma value, a beta value, n, how many times we want to run it, and two seeds to set our number generators. So first, we simulate our gamma 1, gamma 2, and gamma 3 variables, our beta 1, beta 2, and beta 3, and our seeds. Once we do this, we start off with the initial phase. The first part until the while loop. This is the first part of the cycle. This is when you start a cycle. You're establishing an arrival rate for the first step. You're establishing a service rate for the first step. And you're establishing a tau, an L is equal to 1, and a reward. After we do this, basically this is coded in MATLAB, so they were requiring a do loop. But since we do not have a do while loop, I kind of fudged it a little bit. So this is a do loop where it's a while true, so it's going to go on forever unless it's broken out of. So this if statement is a break statement, which is basically ending that do statement. First, you calculate your previous tau. You calculate your new tau based on the min of your arrival and service rate. You calculate the difference between your new tau and the old tau, and you establish your reward based on the difference times the L, how many people are in the system at that certain current time. So if tau is equal to A, you set A to be some function related to clock. If it's equal to D, you're going to set the L minus 1, and you're going to do this. And then you're going to calculate the tau and reward after you break out of that while statement. So the most interesting part of this, and probably the most difficult part of this code, was this clock function. The clock function was kind of hard to find documentation on in Maple, but after some grueling work, we found that we can actually use Simulink to make the clock function in MATLAB. So basically, the clock simulates the simulation time, your current simulation time in the function. This right here is a memory statement. So basically, it loops back to a certain point and calculates the simulation time then. And then this is a sum function where it's the plus and minus, so it'd be this value minus your value in memory, and then it outputs it. So this basically relates your simulation time to the past previous simulation time. There's no built-in function for this in MATLAB, so we had to do it in Simulink. So after running our numbers, we see that as relates to Little's law, it does coincide to around 2.0 for the mean cycle length 0.577, which is a little bit off, because what the actual answer is going to be around more closer to 0.8, 0.9. This can be in part due to my building of the clock function and the covariance A5 value. This seems to be the biggest indicator of where it would be. The covariance between the reward and the tau seems to be the issue whenever we're using this other clock function. So there you have it.